Hello, thank you for having me today. I'm Jongho from the Security R&D team. Today I'm going to talk about a research project we are working on. We are trying to find a way to protect our customer and IT systems efficiently in a scalable way. This talk is about applying machine learning techniques to one of our security problems. Let me introduce a bit of myself before we get started. I'm leading the security R&D team in Line. I study computer science at Stanford and Seoul National University. I'm kind of an inquiring person, so I like to study various subjects, even from humanities and liberal arts. Furthermore, I love to connect them together in interdisciplinary way. And I've been working as a pen tester for more than 10 years in the public and private sectors. The rest of the talk will be like this. We will see what's the problem dealt with in this project and then some preliminaries. Then we'll see how we tackle the pain points. And I'll go over the result of the experiments and the conclusion. There are many things to do to secure the system, and one of the main things we want to do is killing the security bugs, as many as we can, so that fewer people can do malicious activities using our codes. But finding bugs in the source code is a quite sophisticated job. Usually it requires well-trained ethical hackers to do it. The problem is, Line has a gigantic IT infrastructure and a large number of microservices, so relying only on ethical hackers is not scalable in this situation. So we wanted to build an autonomous system to cover some of the jobs. Obviously, string matching using a bunch of regular expressions cannot do the job. So we need something that can understand the source codes. So we came up to use deep learning techniques. In recent years, deep learning has achieved remarkable progress in the natural language area, and it shows better performance than human beings in certain language tests. So we wanted to take an advantage of it. First of all, natural languages and programming languages have similar representations, and programming languages are often considered easier than natural languages. So we think the progress on natural language can be applied to programming languages as well. And we also found there are some previous works of the similar subject. So we decided to use deep learning for this problem. But the problem is deep learning requires a lot of data for training. More parameters often means more power to achieve the goal, but it also means more data for training as well. So if you want to achieve high performance, you may want to increase the size of the model, but you also need to get more data for training. Because of that, nowadays neural network models are quite huge and also data hungry. For example, GPT-3 from OpenAI used 499 billion tokens for training. And it's almost impossible to obtain such amount of bug samples. For example, each bug type, even 100 samples are hard to get. So this has been the most common problem in the security area. Everybody wants to apply deep learning techniques in security, but it's really hard to get the samples for security problems. To solve the lack of trained data problem, we came up with 3 ingredients: transfer learning, meta-learning, and foreign domain data. Transfer learning is for pre-training, the core part. transfer learning has been a good option for low data cases because most of the parameters are covered by pre-trained parameters. It essentially reduces the number of parameters to train. And meta-learning is for optimizing for extremely low data environment by learning some sort of meta-knowledge. We also brought foreign domain data to cover some trainings so that we can build a system with a small amount of data. And let me explain a bit about those concepts. Transfer learning led the heyday of computer vision in early 2010s. Since then, AI outperforms human beings in many computer vision tasks. The main concept is that you can use the parameters from others if the network structure is the same. And the diagram in the slides is a classical example of image classification. The network is composed of convolutional neural network and full connected neural network. The first one is for animal image classification, and the second network is for the vehicle image classification. The early part of the network, the convolutional neural network, analyzes the pattern from the picture. And the latter part determines the actual class from those patterns. So the former part contains a kind of meta-knowledge about how to analyze images. And it must be similar across any image classification task. And using this idea, we can reuse the parameters for different classifications. And with transfer learning, you can use the pre-trained parameters for most of your network and fine-tune the rest of the parameters for the specific task. So the main point is that it requires structural suitability for transfer learning. In the natural language processing area, the network used to highly rely on recurrent neural network, and thus they are quite shallow compared to the models in computer vision. So transfer learning was not possible for NLP because the structure itself wasn't suitable for transfer learning. But since the transformer has been introduced in NLP, the network could be much deeper, and transfer learning came to be possible. The diagram in the middle shows the transformer encoder. The main core of the transformer is self-attention, which is on the left-hand side. In NLP, people started to stack the transformer encoders, and the network is getting deeper. It gets more powerful. And then one of the most successful examples of pre-trained transformer model is BERT, which is on the right-hand side. There has been lots of offshoots of BERT as well because it was so successful. And our system uses Albert, one of the most successful descendants of BERT. And before we get into meta-learning, let's look at the famous computer vision task, few-shot learning. As the name implies, it's about learning with only few data, specifically for image classification. There are two examples here. The first one is two-way one-shot image classification, and the second one is five-way one-shot image classification. Two-way one-shot means that there are two classes for classification and only one image for each class. This kind of task is so easy for human beings. In the first example, there are paintings, one from Jongho and the other from Rembrandt. Once you saw them, you can tell where the painting on the right-hand side belongs to. But image classification usually takes tens of millions of labeled image data for training. So, on the other hand, feature learning is more related to how humans learn something. So feature learning has gotten lots of attention from researchers. And to solve this interesting task, meta-learning has been evolved. The purpose of meta-learning is to find a learner which can be trained faster with few data. So the meta-learning process is learning a learner. And to be a good learner, it must have some sort of meta-knowledge. The diagram in the slide shows an example of data set for meta-training. As you can see, data set consists of meta-tasks or mini-batch for training and testing. In this case, it's three-way one-shot learning task. Each task has an identical setup for the target task. And in this case, the goal of meta-learning is finding a learner which can do a three-way one-shot learning. There are many approaches to do meta-learning, like the black box approach and the non-parametric approach, but we're going to go through the optimization-based approach. The model agnostic meta-learning is the most famous method for the optimization-based meta-learning. As its name implied, it can be applied to any model. So we can use it not only for image classification, but also for our NLP-based model. The formula you see in the slide is a optimization target. Just like the formula, the optimization is conducted on the double loop. Hence, it needs to calculate the Bayesian matrix to find the optimal parameters. And these parameters will be initial value for fine-tuning. So it's kind of hyperparameter optimization problem as well. And since finding a Bayesian matrix requires lots of computation, there are some approximation as well. And we use reptile, which is one of the first order approximation. And as in the formula, it applies the first derivatives into the parameters. In case of the second derivatives are negligible, this approximation works as well too. So we go for the reptile in this case. Now let's see our actual system. This is overall architecture of the system. The overall design is pretty classic for classification task. If you recall the image classification model from the previous slide, the model was a combination of convolutional neural network and full connected neural network. And the convolutional neural network was for image pattern recognition, and the full connected neural network was for pattern to classification. And in the NLP, a similar structure is prevalent using the transformer for classification tasks. So our models are similar to those models, and let's see overall architecture in detail. In the preprocessing, we split the code into chunks and put them in JSON format. Since the transformer model can be kind of fixed amount of data at a time, we need to split the code. And to make data compatible with foreign domain data later, we put the data in JSON format. Then the preprocessed data is fed into the neural network model. In the neural network model, the data turns into tokens. To make tokens, we use byte pair encoding tokenization here. We want to use all the information in the source code, including the identifiers like variable names and function names, but they are often composed of several words. So using BPE, we can handle those words efficiently. So we put the BPE tokenizer in the front. And for the BPE tokenizer, we used sentence piece from Google. And after the tokenization, the data goes into the transformer-based model. As I mentioned earlier, we choose Albert for this. And Albert is responsible for generating proper embedding from tokens. And thanks to the self-attention mechanism in transformer, this also can handle polysemy words, and it generates context-aware embeddings. The rest part is for predicting the vulnerability from the embeddings. So this part is responsible to analyze the code from previous embeddings. This part generates 3 outputs: the start point of the bug, and the end point of the bug, and the classification of the source code. The first and second output is for locating the bug in the code. The model predicts the location probability of each token. Since it masks the probability distribution, there are a softmax layer right before those outputs. The third one is for determining whether this chunk contains vulnerability or not. Since it's a classical classification task, we just put full continuous neural network in front of it. And this diagram shows how the location prediction process works. At the bottom, you can see the tokenized input from the source code. Once they fed into embedding layer, they turn into vector representations. Then they go through all the rest of the layers, and the output is a probability distribution for the starting point of the bug. The bar graph on the top shows the probability of each token. And most of the bug finding systems are classifiers. They determine if a piece of code has a problem or not. But our system is different. We treat the problem like a closed domain question answer problem in NLP. So our system is not just a classifier, but its goal is locating the bug in the code. So a closed domain question answer problem is a kind of reading comprehension problem. So we are treating the bug finding problem as a reading comprehension problem here. And this diagram shows how the training goes. As you can see, training can fall into 3 phases. The first one is pre-training phase. And in this phase, we trained the BP tokenizer and the Albert part with programming corpus. As I already mentioned, this part is for generating context-aware embeddings. So we can train with arbitrary code, which doesn't have to have bug inside. And the training task was the same with Albert. We use masked language model and sentence order prediction task. The second phase is the meta-learning phase. In this phase, the training target is a latter part only. So we froze the front part, then conducted the meta-training. Since we don't have we don't have enough data for meta training. We use data from other domains, and in this case it was English. Hence we put a different tokenizer and Albert accordingly for the data, and to be specific we put English pre-trained BPE and Albert, and used Squad 2.0 dataset for meta training. And we will go about the Squad dataset in detail later. And in the last phase, we do the fine-tuning for the bug we want to find. As you can see, we transfer parameters from the first phase for the former part, and the parameters from the second phase for the latter part. For this phase, all parameters come from other phases, but the first part is frozen, and the only second part is fine-tuned for the task, because the second part is responsible for classification itself. And one more thing that I want to mention is that since the first and second phases are independent of each other, they can be trained parallel as well. Let's talk about the experiment. Our target for experiment was DOM-based cross-site script. Unlike other cross-site script bugs, this happens in the document object model. That's why we called DOM-based cross-site script bug. For other cross-site bugs, usually you can see the malicious code in the server response. But for DOM-based cross-site script, the response from the server doesn't change, since it happens only in the browser. So we cannot use traditional cross-site script scanners to find this bug, and it's more tricky to find it. There are two ways to find the DOM-based cross-site script bug. The first one is runtime investigation in the browser, and the other one is source code auditing. And this experiment is for the latter case. DOM-based cross-site script is composed of a source and a sink. In the example in the slide, the green part is a sink, which consumes the malicious code, and the bottom is the source, which triggers the bug. So the main goal is finding the DOM-based cross-site script sink from the source code. And here's about data set. These are training data set up for each training phases. For phase 1, pre-training, we use HTML corpus from the web. And corpus is a linguistic term, and it means a language resource consisting of large and structured set of text for training. Since JavaScript is often mangled with HTML, and the bug, the DOM-based cross-site script bug, is related to the document object model, the system needs to understand HTML and JavaScript all together. So we used HTML corpus for pre-training in this case. The second phase is where the foreign data comes in. When we meta-train the classification part with different domain data, because to cover this part, and for meta-learning, we use the Stanford question answering dataset, like I mentioned, and the Squad is reading comprehension dataset from Wikipedia articles. It's a different kind of task, obviously, but the task structure are very similar. After all, like I mentioned, source code auditing is also kind of reading comprehension problem, because the bug is in the source code itself, and we just need to locate them. For meta training, we generate meta tasks from the score dataset to find the optimal parameters for the learner. We set the size of mini batch size to 24 in this case. For the last part, fine-tuning, we gathered bulk samples from the patch history in Git repositories. Because we wanted to find real samples, we went for patch history and checked whether the bug is resumed or not. From this, we could get only 29 samples of the bug. Then we split them into 23 for training and 6 for validation. And this is the experiment result. We set the baseline model for comparison. The baseline model has the same structure, but the latter part is not trained. It is just randomly initialized. On the right-hand side, there are two learning curves. The first one is for meta-learning. It's pretty jagged due to the small data size of the mini batch. However, it gets slowly but surely converged to the optimal value. And the second one is for fine-tuning. In the fine-tuning curve, you can see that meta-learned model converges faster than the baseline model. And the table on the left is a result score of the baseline model and the meta-learning model. There are training scores and test scores. The training scores doesn't much have difference, but the test scores are quite different. There are two scores here, EM scores and F1 scores. EM scores and F1 scores are standard metric for QA programs in NLP. The EM score means exact match score, and the F1 score means the harmonic mean of the precision and recall. So the EM score is calculated based on the whole answer, but the F1 score is calculated based on character by character. Comparing the F1 score, we can see that our model has a 45% gain in performance. So is it promising? We don't have an F1 score of human performance in this task. We have one in Squad 2.0, which is 89. Since they are two different tasks, we cannot compare the score directly. But we may expect that around 90 is a reasonable bar to be confident with. So our F1 score of 40 might look not good enough, but there's a good excuse for the low score. In deep neural network, the size of parameters matters. As I mentioned earlier, more parameters often means more power. In the case of GPT-3, they also conducted few-shot learning for Squad 2.0, not for bug finding. And then they got 32 with 125 million parameters, and it gets increased up to 69 with 175 billion parameters. So again, more parameters, better performance. And for the record, our model got 40 with only 80 million parameters. So the takeaway of this experiment is our ingredients can improve the performance without increasing the size of the parameters. And this is a graph about the parameter size of transformer-based models. You can compare the size of the model here. As you can see in the graph, since 2018, the size of a transformer-based neural network has been increased exponentially from 94 million to 175 billion. And their performance also has been improved dramatically. On the other hand, our experiment model, I already mentioned, has only 80 million parameters. It's about 5 times smaller than Elmo from 2018, and it's about 4 orders of magnitude smaller than GPT-3. This means we have many rooms to increase the performance in terms of parameters. And our score, 40, is still higher than the GPT-3 with 125 million parameters. So let's see the conclusion. The thing that transformer-based model can also work well on programming languages has been already studied by others. But the transformer-based models require lots of training data because the model size is very deep. Even we use transformer learning, there are still lots of parameters to train. And meta-learning algorithm is useful for small data problem, and it's a huge point for security problems because we are suffering from small data challenge when we want to use deep learning techniques like anomaly detection or some kind of classifications in security. And the last point, the data set from other domains can be used for meta training if there's a structural similarity between the data sets. So we transform the source code auditing task into a reading comprehension problem. Then we use the reading comprehension data set for meta training. So there are many things to improve here. First of all, we want to find more ways to improve the performance without increasing the number of parameters. Training deep learning model are quite expensive. The famous GPT-3 shows wonderful performance, but its training cost is way too expensive. According to one estimate, it would cost 355 GPU years and $4.6 million for a single training. So we want to explore more about the structural characteristic of programming language so that we can leverage this characteristic for better performance without increasing the parameters. We also want to investigate more on long-term dependency because the source code can be very large and it may depend on the code from other files or other libraries. So we want to handle them properly to find more tricky bugs. And for the last, we want to extend the capability to other languages and other bugs. It would be very interesting to see how fast it can be tuned for different languages or different bugs. And we are also considering an ensemble model for better accuracy. And this paper, the paper about this project has been presented at EICC 2020, and you can find more details from the paper. Thank you.